Greetings, Earthlings. My hair is getting crazier, and I don't care because it was my birthday. Alright, so today we're going to go into triangle and parallelogram proofs. We're going to cover a lot of stuff. This is not going to be just your granddaddy's triangle proof video. One of the big things you'll see in this video is that I will try to actually give you guys complete proofs. So I don't mean complete as in I'm going to finish them, but the sketch of the proof that I would give you guys would work as a full proof. So what do I mean by that? I mean that a lot of the proofs you're going to find, they don't actually prove what they're claiming they're proving. So that'll become more apparent in a second. So let's just dive in. So let's say we have a triangle, and before even that, let's just say we have a rectangle. So this is a 4 by 5 rectangle. Let's just review why, if this is, let's say, the length and the width, or the base and the height, why is the area of a rectangle? So that'll be area of a rectangle is base times height. I get confused about this myself on occasion, so just as a refresher, we can think of this as little boxes. And we are literally splitting this up into 4 rows of 5 columns. So when we multiply 4 by 5 and get 20, that's the rationale there, because we've split it up into little 1 by 1 squares. So that's why the rectangle works, and we're clearly going to be using this box of just base times height all over. Alright, so when I say the box technique, that'll be a very frequent thing in this video and in the next few videos. So I'm just going to say, very frequently, just put it in a box. So when I say that, I mean put it in a rectangle of the right size. Alright, so the right triangle, also notice, for the triangles, when I say complete proofs earlier, what I'm referring to is a lot of proofs don't consider these 3 cases. They'll just give you one of these cases, typically, let's say the acute case, and call that a day. Now, that's fine, but as a kid, I was always curious what happens in the other cases. So, same thing with the parallelogram. You'll often find many proofs will look at this case and give you this diagram, but I've wondered what happens in this case. So that's why I want to try to give you guys kind of a better presentation than what you'll normally find. So let's start with the right triangle. So if we have a right triangle, this is the height, this is the base. So we're going to put it in a box. So in this case, it's easy. We just put it in a box like this. And then without doing anything fancy, we could see that we could fit 2 of these triangles. So if we flip it this way, right, we fit another one of them in here. And hence we have 2 of them in an area that's base times height. And so for at least this right triangle case, the area of the triangle would be 1/2 base times height. So that's this simple case. Now let's take the acute case. In the acute case, we have a triangle that's, let's say, like this. Now notice also, I'm trying not to draw this so that it looks isosceles. These 2 lengths look a little bit different. Why? Because if you draw it such that they look the same, that's not a very general proof. Because you might say, hey, are you sure this is still going to hold if these sides are not the same? So that's a very important point when you're doing math proofs. You don't want to assume anything in particular, because then your proof is going to have that assumption built into it. So if you want a powerful proof, you want to assume as little as possible. So again, we're going to put this in a box. So what sort of box should we use? Well, we'll put it in this size box. Now, this is not as obvious that this triangle is 1/2 the rectangle, but if we chop it, then we could see that this left side is the same area as this triangle if we were to flip it, and this triangle has the same area as that triangle. Therefore, together these 2 have the same area as these 2, and therefore there's 2 of these triangles in that rectangle. And so in this acute case, we again find that the area of a triangle is 1/2 base times height. Alright, let's move on. Obtuse triangle. So in the obtuse triangle case, let's say it looks like this. We are going to, again, this is the base. The height is not any of these, but this is going to be the height. It's always the perpendicular distance. So in other words, if we were to drop this down to this projection over here, this imaginary point here, that would be the height, not this and not that. All right, so that's our height. Now, I'm going to show you guys the traditional proof first, and then give you guys some of my thoughts. So the traditional proof would say, okay, let's just say this segment over here is an x. So this from here to here, that's an x. So we already proved, by the way, let me back up a second. Whatever techniques we use here, we'll use in the subsequent videos too, and the idea here is we're trying to build a hammer. Notice how I've split this up into 3 cases. We don't want to start with the obtuse case because that's a harder case. So oftentimes when doing math proofs, you want to start with something simple and use that as like a sledgehammer to, smash the harder cases. So in the same way, we are going to use the fact that we already proved this right triangle case to find the area of this large triangle. I can give it letters, A, big B, big C, and let's just call this point D. So triangle ABC, the area of that we already know from this case, and that would be the entire base, which would be 1/2 of B plus X times the height. Now that's the area of all of this, but then we don't want this piece, so we're going to subtract that off, and the area of this piece, again, because we've already proved the right triangle case, and remember this is our right triangle, so triangle ABD, the area of that is X is your base now, H is your height. So 1/2 of XH. Now if you do the algebra here, if you distribute the H, you're going to get a 1/2 BH plus 1/2 XH. And these XH's will cancel. So when you do that, you will get exactly what you want, which is 1/2 base times height. So that's the traditional proof. It still uses the idea of a box, but not really. So like I've never really been happy with this, and this is what it's usually presented in school. I've always wondered, can we find something nicer than that? So let me explain why I'm not happy with that. So it works, it's correct, because we're sort of using the box, but we're just using the fact that we already proved it for the right triangle case. We have to use some algebra, so it's not really that intuitive to do in your head. And then we're also working backwards by subtracting. So we found the whole triangle minus this triangle to get the remainder part. Now it's not too bad, it's still a pretty nice proof, but I've always wondered, is there like a cleaner proof for this obtuse case? So stay tuned, and we're gonna come back to this point in a second. So first let's keep going to the parallelogram with this box technique. So for the parallelogram, this is your normal case. So you get a parallelogram that's fatter in the width, and then you're told, okay, we can chop this triangle off and move it right over here. And guess what? If this is your base and the height is like that, then you've created a box, and therefore the area of your parallelogram in this case is base times height. Okay, so that's very nice. However, I've never thought that to be a complete proof. Why not? Because what happens if your parallelogram, and by the way, if you in school or if you look online, that's usually the proof you're going to find. If you look at this case, so let's say we have something that's like that. Okay, so again, it's a parallelogram. These two sides are parallel. These two sides are parallel. We can indicate it if we want. So the one arrow means these are parallel, and the two sets of arrows means that these are parallel. All right. Now, if you try to do what we've just done in the first case, you can't really cut it because you can't cut it all the way down because there's nothing over here. So that's not going to work. That's why I said that I'm trying to present complete proofs to you guys. So, but let's try it anyway. So let's just say we go to the edge here and we do a cut like that. All right. So then theoretically we could take this trapezoid looking thing and move it to the left. So this is going to move right over here. That's going to move over there. and this segment's going to basically become this segment, right? Just move to the left. So hopefully you guys can visualize that this piece became this dotted piece. Now once you've done that, then you could chop this triangle off and put it here, and then you get the box. It's not too bad, but I just really want to emphasize that, you know, this is the difference between saying like, oh, this is where math gets its kind of prestige and notions of being rigorous, because as you guys can tell now, this first case doesn't prove the whole thing, because the second case is a bit trickier to construct. All right, so that's the box technique. Whatever your shape is, we try to put it into a box because we know that the box is just base times height, and then we find that for a parallelogram, it is base times height. For a triangle, it's 1/2 base times height. So we try to find some fraction of the base times height. All right. Now to the more non-traditional part of the video. Thanks to my friend Jan, he mentioned, because I asked him this question, I had a few ideas, but I said, you know, what's another way of proving this besides the well-known proof that I just showed you guys? So, here's our obtuse triangle, meaning that this angle is more than 90 degrees. And let's say here is some other triangle that is acute. And let's say these bases are the same. Now there's something really cool called the Cavalieri Principle. So I should add the word principle. And what this says is, if the shapes have the same cross sections at every height, then the areas are the same. Now it works in 2D and 3D. I'll just use it in 2D. So let me explain what that means. If we do all these cuts, so if the area of this cut is the same as the area of this cut, and the area of this next cut is the same as that, basically if slice by slice they all have the same areas, then together the sum of them will also have the same areas. So what is the kind of like, why do we care? Because instead of trying to prove this obtuse case, which is a bit tricky, we could just say, all right, construct an acute triangle where each of these slices will have the same areas as that. Now that may not be super intuitive, but hopefully a lot of you guys can kind of just run with it. I'm just presenting an idea, and you can get more in depth if you like. So what we're going to do is basically deform this. If we were to just squash it over, right, basically move all of this over, we would get a triangle like that. Imagine this is made of like Jello or something. So then all these would have the same area. So by the Cavalieri principle, this obtuse case would just reduce to one of these right or acute cases. All right. Now, that's just an idea just so you guys are familiar with that principle. We can do the same thing with the parallelogram. So that's the Cavalieri way of proving the parallelogram. You can take your parallelogram and you could take a rectangle. Now, as long as each of these has the same area as each of these, we can basically move this over to align it, right, so that this parallelogram just becomes that. And if little piece by little piece they all have the same areas, that in total the sum of these will be the sum of all of those. So that's another fairly intuitive and nice way to show that the parallelogram is base times height. All right. Next, so thanks Jan for that idea. All right. Now this next idea is thanks to a student of mine, thanks to Max. And if we have this obtuse triangle, so what was my kind of initial goal? I was saying, just as a challenge, can we prove this case without using either algebra or working backwards? Just kind of doing the same business we did here. So let's take our obtuse triangle. And here was Max's cool idea, which is take this triangle and flip it so that it goes like this. Right, so you basically rotate it 180 degrees and stack it. So if you take two of them, then we've created a parallelogram. And now that means we are in this case, which we've already proven. So if two of these create a parallelogram, which we know is base times height, then one of them is 1/2 base times height. So I really like this. That's really cool. So thanks, Max, for that one. All right. Now, let's go to the parallelogram again. This one is also, this is the triangle idea. So by the way, when I use these parallelogram and triangle boxes here, that's what I would call the shape technique. So this is the box technique, that's the shape technique. So we either break it down or build it up into nice shapes. So rather than considering two different cases, we can just split this into two triangles. So that's the base, that's the base, that's your height. And then I won't prove this super rigorously, but I think many of you guys can convince yourselves that these two triangles have the same areas. So instead of proving the parallelogram, we know that each one of these is just an acute triangle, which we've already proven. So that would be 1/2 base times height. That would be 1/2 base times height. Add two of them up, you just get base times height. So that is a very nice way to prove the area of a parallelogram. All right, finally, this is the craziest part of the video and the challenge part. So if you're not very advanced, you may just want to kind of tune out at this point. But if you feel like, hey, this was sort of easy, I really want to challenge myself, or if you're a teacher, you want to give a very advanced exercise, this is something you can try. Now, I should warn you guys. And be honest that I have not completed this proof myself. So this is an original proof I came up with. It's potentially a proof. It may not work. I feel like it would. In the time that I tried to complete it, I was unable to complete it. It turned out a little messier than I thought. Now, I'm fairly confident. I'd say 80 to 90% that it can be done. But I'm going to leave this as an exercise. So if any of you, whether it's just like students, parents, educators, anybody on the internet at all, if you want to complete this, that would be fantastic, and maybe write it up or post a video. I'm just going to present you guys the sketch of this idea, and you guys take it from here. So also, I should indicate this proof is like way more trouble than it's worth. So we really already have plenty of ways to prove this stuff. So this is for just fun and enrichment. It's not really like this is the best way to prove it by a long shot, but it's just a fun exercise. Just like in working out, sometimes you want to make your life harder just for fun to train, All right, so for creativity's sake, I'm presenting this. So let's say we have this obtuse triangle. I'm going to call this let's call this your original base. That'll be base 1. And this entire thing is your height. Now, the idea here is to leverage the right or acute triangles. So I'm going to try not to involve, well, we're going to still have to involve a ton of algebra, but I'm going to try to do this as a direct proof with no working backwards. In other words, no subtractions. So I'm going to go, I call this the infinite ladder proof because I'm literally just going to go up perpendicular in a ladder fashion, like this, zigzagging. Now, hopefully you can convince yourself that if you were to do this, the lines are going to get smaller and smaller. So while it may seem like, oh, it only take a few steps, it'll probably, it seems, it's going to take an infinite amount of these things because they're going to keep shrinking. So if you were to zoom in on it, you'd have a lot more to go. All right, so let's call this base 1. We'll call this segment base 2. Base 3, and so on. So this height will be, let's call it H1, the first height, H2, this will be H3, and so on. So here's the sketch of the proof. What you would do is show that the sum of all of these little triangles, if you add it up, gets you just 1/2 base 1 times the height, the base times the height. Now, I'll throw out some ideas on how to do that, but like I said, it's largely a bit of an open problem. I just don't have time to dedicate to complete this proof, but I think it would be a really neat exercise for a very advanced student or teacher or parent. Okay, so also what we're going to need here is the sum of a geometric series. So if you don't know how to do that, look at my channel on find the video on how to sum a geometric series. So we have two sets of triangles. We have these triangles, and then we have, I'm going to give these two dots, these triangles right here. And all of these triangles are similar. So we haven't covered similar triangles on my channel yet, so that's why I'm kind of jumping the gun on a lot of stuff here, but I want to present it anyway. So essentially we would add up base 1, h1. So the area of this triangle would be 1/2 of base 1, h1. Now I'm just going to factor out this 1/2 so I don't have to keep writing it, plus base 2, h1 plus h2, b2, or let me just write it base 2, h2. All I'm doing is summing the area of each individual triangle, which happens to be a right triangle, so we know how to find its area. Now, the idea is that by playing around some equations, so I'll give you guys an idea of what I mean. This triangle is similar to that triangle, so what that means is h2 over b2 is equal to h1 over b1. So this height is to that base, like this little height is to that little base as this medium height is to this medium base. They're proportional. They share these angles. They have a 90, so these angles are the same. So you can convince yourself that all of these are just scaled versions of they're all proportional triangles. So what are we going to do with this? Well, you can create a substitution and find like base 1 in terms of base 2 or whatever. So you can get a lot of things going and try to plug stuff in. The hope and the idea is once you've done some substitutions and some clever algebraic manipulation, you will hopefully find something that involves a lot of these heights. So let's say you get h1 plus h2 plus h3 all the way up to like the infinite little height. And the sum of all of those happens to be the full height. So that would potentially be a proof, and I'm not going to finish it, but like I said, this is a challenge. Have a go at this. If you think you have if you think you figured it out, either write it up or make a video. I would absolutely love to discuss that and look at that. All right, I'm going to see you guys in the next video. So the main thing here is not so much what is the formula of the triangle and the parallelogram, but what are these techniques, and focusing on how are we thinking about this, the process, not just the proof. So I'm going to keep emphasizing process, 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 and not just the proof. All right, I hope that was fun and not just another triangle video. I'll see you guys in the next video.